Welcome back to Probability and Statistics 1. We're in Unit 3 discussing the fundamental concepts of discrete probability spaces. And in this little video, I'd like to introduce the important concept of a random variable. A random variable is essentially some kind of measurement of the outcome of a random process. So, for instance, if you toss a pair of fair dice, right? What's going to happen is you're going to get two numbers, the outcome on dice 1 and the outcome on die 2. You can think of a lot of different things that you could measure from that. For instance, you could measure the sum of the two dice, or the product, or the difference, or the maximum of the two dice, and so on. All those would be random variables. And in some sense, probability is about random variables. So what exactly is a random variable from a mathematical point of view? A random variable is simply a function defined on a sample space. So if you have a function defined on the sample space of a probability model, you've got a random variable. We classify random variables in terms of the range of that function. So if you've got a function that takes outcomes and maps them into real numbers, that would be called a real valued random variable. If more specifically the function takes outcomes and maps them to integers, it'd be called an integer valued random variable. You can also have vector valued random variables and so on. Our notation for random variables is a little bit different than normal function notation because we basically suppress the argument. So capital X here will be the sort of standard name I give to random variables, capital X, capital Y, things like that. And usually I'll just write that, not capital X of S, even though that would be that would be correct because X would be a function on capital S. So let's take a close look at one example, and as I said, basically from this point out, we'll be looking at example after example of random variables. Let's look at the dice tossing example. So we're going to toss a pair of fair dice and record the value of each, and we've seen this sample space before, the 6x6 grid containing all possible outcomes. And let's think about these random variables. X is going to denote the sum of the two values, Y is going to denote the first value minus the second, and Z is going to denote the maximum of the two values. So X, Y, and Z are what we call random variables. And this is usually the way I'll define a random variable, by saying what it is, right? Of course, we could write it as a function, and there you see it. If I call my outcome I comma j, then x is just the sum of those two values, so I plus j. Y is the first minus the second, so I minus j. And z is the maximum of I and j. So you could write them in function notation, but typically we're not really that interested in that so much as questions like, what's the probability that the sum is 7? Or what's the probability that the maximum is 4? And in fact, to really understand a random variable, you want to ask yourself two things. What are its possible values? And what is the probability that it takes on each of its possible values? That probability would give you what we call the probability mass function for the random variable. So let's think about the first random variable we defined, the sum of the two dice. The possible values I'm going to denote again by this set S, but I'm going to use a subscript of X to denote that this is the possible values of X, the random variable X. And of course, the possible values of the sum of two die are the integers from 2 to 12. And we already know that all the combinations in the larger sample space of all the 36 different outcomes have the same probability, which is 1 over 36. And so we can use that to find the probability of each outcome for x, right? So the probability that x is 2 is just 1 out of 36 because it corresponds to that single outcome of the first die being 1 and the second die being 1 in the larger sample space of all outcomes of the experiment. The probability that x is 3 would be 2 out of 36, right? Because there's two outcomes that make up that event, 2, 1, and 1, 2. And similarly, the probability that 4 is 3 out of 36, 5, 6. The probability that it's 7 would be 6 out of 36, and then it starts going down again until when we get to 12, that probability is the same as the probability of a 2, which is 1 out of 36. So in that way, by sort of pulling back and looking at the sort of overarching sample space for this experiment of casting two die, we can derive the probability mass function for x. And here you see it in tabular form. We list the possible values in the first row and then the probability of each of those values in the second row. And that function is called the probability mass function for x. So as an exercise, you verify that this table gives us the probability distribution for y, the first die minus the second. And similarly, you can go through a similar sort of exercise and verify that the probability distribution for z, the maximum of the two dies, is this here. And you should do that because this kind of technique of deriving distributions by sort of looking at the big sample space of the experiment is an important one. Here we have some more discussion questions. Again, I hope you'll take a look at this. These are all things you can answer based on what we've discussed so far, and we'll discuss those further in class. That's it for now. In our next video, we're going to introduce the important notion of expected value, which is the average value of a random variable. And once we have that, we'll be able to really get going in our study of random variables. So until then, y'all take care, and I will talk to you soon.